This video is on collision theory. So when we're talking about rates of reactions, we need to understand what the collision model or the collision theory is. So the theory obviously first states that molecules must collide to react. So I know that sounds obvious, but we have to state this, that if your molecules don't actually hit each other, no reaction can occur. So related to this is that rates of reactions are affected by concentration and temperature. And we're going to talk more about how later on in a later video. And this collision model provides a molecular explanation. So molecules must collide to react. And I hope this makes sense that the greater the number of collisions, the greater the rate of reaction. So the more collisions that exist, the faster your reaction can occur. So concentration relates because the more molecules you have, so the higher the concentration, right, the more moles of solute you have, the greater the probability of a collision, which would increase the rate, right? More molecules, you're going to have more collisions. The temperature increases the kinetic energy. So the higher the temperature, the more kinetic energy, and the more likely they are to collide, because you're going to have molecules that are moving faster with more energy. So just because molecules collide, however, does not mean they will react. So only a small fraction too. So there's a few things that we have to consider when we're figuring out will they react or not. So one is that they have to obviously collide with each other. Two is that they have to collide with enough energy, and we call this activation energy. And the three is that they have to collide in the right orientation, meaning they have to hit in the right way. So that's kind of like their puzzle pieces. And if they don't hit in the right way, they won't fit together and actually do anything. So let's talk about the energy first. Activation energy, and that's this E sub A right here. Make sure you know this symbol. So the energy of activation, right? Capital E is energy. The subscript A is for activation. It's the minimum amount of energy needed to react. So this is supplied by the kinetic energy of the molecules. So the molecules have to be moving fast enough, which means they have to be at high enough temperature to have enough of this kinetic energy. So this minimum amount, it's different for every reaction. And the typical arrangement of the atoms at the top of the barrier is what we call the activated complex or the transition state. So when I get to the graph next, I'll talk about this more. But what I want you to note right here is that transition state is the term that IB likes more than activated complex. So we'll mostly use transition state, but you could read in other things activated complex. All right, so when it comes to activation energy, we can look at these enthalpy diagrams. So if you remember last chapter, you looked at an enthalpy diagram just like this. We're just adding another piece to it. For example, if we had an endothermic reaction, like this first one here, right? If we had our energy or our heat here, we would talk about our reactants being here. The energy, when it increased, right, you'd go put it in as an endothermic reaction, and your products would end up here, and your delta H would be whatever it is, some positive value. So that relates to this right here, but what we're doing is we're adding this piece in the middle. This, we could call it a hill, we could call it the hump, but how do you get from reactants and products? All right, so in an endothermic reaction, you can see your reactants, right, are down here, your products end higher, because your delta H is positive. But the new piece is this right here, this activation energy, this E sub A. And the way you always measure this is E sub A is measured from reactants to the top of the, and I'm gonna call it the hill. Okay, so you're going from here, right here with your reactants, all the way up to the top right here. That's the amount of energy. That's the minimum energy. Obviously, if you have more than that, this will react. But if you don't have that minimum, nothing's going to happen. No reactants turn into products. In an exothermic reaction, you can see same idea. We've got, right, our reactants here. Our products are lower. Our delta H is negative. But what we're looking at here is a much lower activation energy because your, oops, sorry about that. Because your reactants are already starting out higher. So you're going from here to here. So it's a much lower E sub A, which is why exothermic reactions are much more likely to happen on their own. They need much less energy added into them. So the delta H itself has no effect on the reaction rate. So how fast the reaction happens has nothing to do with the delta H. But the lower the activation energy, the faster the reaction rate. And this is something you should already know. If a forward reaction is exothermic, the reverse reaction is endothermic. So if you remember when we did like Hess's law, for example, and we would reverse a reaction, the delta H value would, or not the value, the sign would change. All right, so let's talk about this Maxwell-Boltzmann distribution. So in this graph right here, we've got energy now on our x-axis and our number of molecules on the y. So what we have here is we have, I'd like you to note that the area under the curve equals the total molecules. Okay, so to actually calculate that, you'd have to do calculus, and we're not going to do calculus. But that's what we're looking at, is this area under the curve is how many molecules we have in our reaction. So as we go from left to right, we're increasing the energy. So you've got to get to this point right here, right, to hit your E sub A before your molecules actually react. So like in this situation right here, these molecules under the curve right here, only these would react. Okay, so I'm going to make a note. Only molecules under curve and past E sub A will react at whatever this temperature is. I'm just going to label this temperature 1. Now what can happen is, though, if we increase our temperature, what do our molecules do? So if I increase my temperature, my curve is actually going to look different, because if I increase my temperature, my energy is going to increase, right, which increases the temperature, and my curve is going to look more like this. So I'm going to label this T2. I'm going to make a little note over here that T2 is greater than T1. So what does this mean? What happens when I increase the energy? Well, now look at how many are under the curve and past the activation energy. Look at these. That's a lot more molecules. So if temp increases, we have more area under the curve past E sub A, so more molecules. Oops. Oh, come on, pen. React. All right. So the last thing I want to talk about with this is how they collide. So we call this the geometry of collision. So think about this this example right here. I've got NO2. So NO2 would be N with 2 oxygens like this. CO would be C to O. And what we're looking at is how these two molecules can hit each other. And the way they hit, like the sides that actually hit each other, determine if it reacts or not. So I've got 4 situations here, kind of 4 combos. So if you look at the first two, I've got C to O, and the O side is coming up from the CO to the NO2 molecule. So if you have O next to another O from the NO, in this situation right here, there's no reaction that occurs. Just like in the next one, if the N was on the other side, this also wouldn't occur. Okay, so then look at this one, look at C. What if it's flipped around and the C side hits the N? That's not going to occur. Here's what actually happens. Look at, if I go back up to the equation, what we're looking at in this reaction is an O from the NO2 has to go over here, but bonds with the C, because you're going to be left with this NO, and you're going to have CO2, where you're going to have C, and they're actually double bonds, but that's beside the point right now, with an O on either side. So the C and the O have to hit each other, which is what you have in this situation right here. So if the C and the O hit each other, that's when a reaction can occur. You can see that doesn't happen here, O to O, it doesn't happen here, O to O, and it doesn't happen here, C to N. So the orientation is the last piece. in the collision theory. So if you've liked this video, please like and subscribe to my YouTube channel.